Okay, so starting with the topic, that is deadlock detection. In the previous video, or in the previous one, we have seen the deadlock avoidance and deadlock prevention. If the system is not using any deadlock avoidance and deadlock prevention, then deadlock situation will occur. Okay, so deadlock prevention strategies are very conservative, as we have seen in the last video that these strategies are very conservative, and this they try to solve the problem of deadlock by limiting access to resources and by imposing restriction on the processes. Okay, the thing what we have learned in the last video about the dead deadlock prevention and deadlock avoidance. Okay, so these two techniques are very conservative. They have lot of restrictions. So they have lot of restrictions. They limit the access to resources, limit the access to resources also. Okay, by imposing restriction on the process also. So deadlock detection approach does not limit. Our deadlock detection approach, this approach does not limit resources, does not limit resources. Okay, or restrict processes action, or restrict processes action. Okay, so it does not limit the resources, it does not restrict the processes action. Which one? The deadlock detection. Okay, the two which we have seen in the earlier video regarding deadlock prevention and deadlock avoidance, they are very conservative. Okay, so we were just taking the flashback of the previous two topics. Okay, so deadlock detection approach does not limit resources access or restrict process actions. With deadlock detection, request resources are granted to the processes whenever possible. Okay, so whenever possible we allow the processes to access the resources. Okay, so the deadlock detection algorithm, we have the deadlock detection algorithm. We'll see deadlock detection algorithm. Okay, so we have deadlock detection algorithm of two types. Okay, these two types are nothing but for a single instance of each resource type, for single instance of each resource. Okay, this is for multiple instance of each resource type. Okay, so a deadlock detection algorithm is basically divided into two algorithms. One is for a single instance of each resource, and the second is for multiple instance of each resource. Example, okay, for example, this is the resource R, so we have only one instance of a resource. Okay, and for multiple instance, it means that for the same resource we are having multiple instances. Okay, so we have these two algorithms. So in this video we are going to concentrate for a single instance of each resource type. Okay, so what we are going to do, how we are going to detect the deadlock? We are going to detect the deadlock by drawing a wait for graph. Okay, we are going to draw wait for graph chart. Okay, and how we can obtain this wait for graph? We can obtain this wait for graph using resource allocation graph. Okay, so using resource allocation graph. Okay, so we are going to detect the deadlock using wait for graph. Okay, if we find a cycle in that particular graph, then we can say that the deadlock has occurred. Okay, if there is no deadlock, If there is no cycle, then it means no deadlock. And how we can get this wait for graph? We can get this wait for graph using resource allocation graph. Okay, now let us see. We'll take one example and then we'll draw it, and then we'll come to know how we can. Okay, so this is a sample graph. I can say this is the resource allocation graph. Okay, resource allocation graph, this is called the resource allocation graph because we have all the processes over here, we have all the resources over here, and we have make the ages also. Okay, so we can easily see that for we are having process 1 2 3, process 4, and this is process 5. Okay, so total 5 processes, and total resource r1 r2 r3 r4 and r5, total 5 resources I have. Okay, so we have some edges, the direction as given. Okay, it means that p1 is holding resource r2 and is waiting for the resource r1. Okay, has a requirement of resource r1. R1 is being held by the p2 and is waiting for the r3 r4 and r5. Okay, p3 is holding r4, p3 is holding r4 and waiting for the r5. Okay, so p4 is holding r5 and waiting for the resource r2. Okay, p5 is holding r3. Okay, so this is the situation. This is called the resource allocation graph. Okay, so resource allocation graph, from resource allocation graph we have to create wait for graph. Okay, we have to convert this graph into wait for graph. Okay, why we are converting this into wait for graph? Because from wait for graph we will come to know that whether there is any cycle or not. If we found any cycle, then it means that there is a deadlock. Okay, so for deadlock detection we are converting this resource allocation graph into wait for graph. Okay, so how we'll convert it? First let us know. Okay, so first of all we are having total 5 resources. Okay, so I'll draw 5 resources. p1, this is p2 on the same place, p3 over here, then p4 over here, and p5 over here. Okay, now for p1. Okay, so p1 is holding resource r2 and waiting for the p1 is holding the resource r2 and waiting for the resource which is being held by the p2. Okay, it means that simply p1 is waiting for the p2. Okay, so in the simple meaning of from this point to this point, we can say that p1 is waiting for p2. Okay, so simply I can direct in this way. Okay, so I'm just simplifying the direction, the diagram from resource allocation graph. This is resource allocation graph, and this is wait for graph. Okay, so this is wait for a graph. So we have p1 which is holding r2 and is waiting for the resource r1 which is being held by the p2 is holding resource r1, and waiting for p5 also. Okay, we waiting for the resource r3 which is being held by the p5. Okay, so indirectly we can draw the line from here into this direction. Okay, so we have done with the p2. P2 is also waiting for the resource r4 which is being held by the p3. Okay, p2 is also waiting for the resource r4 which is being held by the p3. Okay, so indirectly p2 will direct to the p2 is waiting for the p3. Okay, then again p3 from p3 is holding r4 but is waiting for the r5 which is being held by the p4. Okay, so p3 is indirectly waiting for the p5, so we can make the direction in this way. Okay, now the last is remaining p2 to p4. So p2 is waiting for the resource r5. Okay, p2 is holding resource r1, p2 is holding resource r1 waiting for r3 r4 and r5. Okay, r5 is being already held by the p4. Okay, so indirectly p2 is waiting for the p4. So p2 is waiting for the p4. Okay, then again the last one is remaining. p4 is waiting for r2. Okay, P2, sorry, P4 is waiting for R2, which is being held by the P1, okay, which is already holded by the P1, okay. So indirectly P4 is waiting for the P1. This is the simplest wait for graph we can draw, okay. Again, I'm just revising what we have to do. We have to remove the edges. Okay. We know that we are having different kinds of edges. The one edge is a claim edge. Second is the request edge, okay, and the third is the allocation edge. The claim edge is represented using a dotted line. The request edge is represented using a solid, and this one is from solid line, okay. So first the edge remains the claim edge. After it is converted into the request edge, and then it is converted into the allocation edge, and again then it is converted into the claim edge, okay. So we are converting the resource allocation graph into wait for graph, okay. I'll give an example. Your P1 is holding resource R2. P1 is holding resource R2 and waiting for the resource R1, which is being held by the P2. So indirectly P1 is waiting for the P2, okay. So instead of going from over here, we'll directly point to the P2, okay. So while converting it from resource allocation graph to the wait for graph, we have to remove all the request stages and assignment edges, okay. So we have to remove all the request edges and assignment allocation, not assignment edges or allocation edges. So we have to remove these two kind of edges, and we have to put the claim edge, okay. So so this is how we can say that we have converted it from the resource allocation graph to wait for graph, okay. Now in wait for graph, if you will find any cycle, then you will come to know that there is a deadlock, okay. If there is no cycle, then we can say that there is a deadlock or not, we can easily find out, okay. Okay, let us just find out. P1 is waiting for P2, P2 is waiting for P4, and P4 is waiting for P1, okay. There is a cycle, okay. We can say that, okay, there is a deadlock. P2 is waiting for P3, P3 is waiting for P4, okay, but P4 is waiting for the P5, okay, and P1 is waiting for the P2, and again P2 is waiting for the P3. So again you can find there is a deadlock, okay.